In a previous lecture, we look at numbers that can be measured with no error at all. That's an unusual situation. Most of measurements we perform contain some sort of error. You can look at it in detail. Word error is not the only word we use to describe uncertainty. Sometimes we use deviation, for example, standard deviation, but that's essentially the only example. Most common word is uncertainty of number. Sometimes we say about error. The same can be described by the word mistake, but we reserve mistake for something we are doing absolutely wrong. Now, the result always should be your estimate of value, so what you did, and plus minus some uncertainty. For estimate, we usually use mean or average, which is the same, but this is not the only way to have your result estimated. We have three major sources of numbers. Numbers can come from counting. Numbers these days are often coming from digital display. You just read the numbers, or you can download these numbers into your processing unit, so in computer, laptop, tablet, whatever. Or you can have analog scale. For example, you are using simple spectrophotometer and you read the scale. Same you can do with your burette, with your pipette and many other instruments. They are usually inexpensive and fantastically reliable. Now, how we classify components of uncertainty. The result of the measurement is only approximation or estimate of the value of specific quantity which we measure. Thus, the result is complete only when it is accompanied by quantitative statement of its uncertainty. So we need to provide number of uncertainty and much better add some description how it was calculated. The uncertainty of result of measurement consists of several components which may be grouped into two categories. Type A, evaluated by statistical methods. The example standard deviation, we'll look at it later. And type B, evaluated by other means. There's not always simple correspondence between classification into categories A and B. Commonly we say that A is random and B is systematic, but this is somehow oversimplification. We'll start our study with type B. Type B evaluation of standard uncertainty usually based on judgment using all information available, which may include previous measurement data. You or somebody else measured the same thing before. Then experience with or general knowledge of behavior and property of this material. Type B error may come from manufacturer specifications or from data you did for calibration yourself. Now, some uncertainties are assigned to reference data taken from handbooks. For example, atomic mass of neon is 20.1797, with 6 being uncertainty in the last digit. This is taken from the reference book. We are not going to check it. and we can use this uncertainty for our further calculations. Let's look at uncertainties, type B uncertainties, coming from our usual devices. Analytical balances usually have type B uncertainty of 0.1 milligram. As micro balances that we are not going to use in our lab can have slightly smaller uncertainty, 0.04 milligrams, and we can read 0.01, but the real error is slightly larger. Volumetric flasks have their own tolerances. So, for example, 10 milliliter volumetric flask has tolerance plus minus 0.02 ml. Same tolerance is of Class A transfer pipettes. Class A, by the way, means that's high quality flasks and pipettes. Type B devices will be cheaper and will have twice larger uncertainties. So when we look at scale, we'll see that actual reading will be 10.00. Then between 998 and 10.02 you have some area where you do not know where the actual value is. This value will say that this is uncertainty or uncertainty interval. Uncertainty alternatively can be given as interval between 998 and 10.02 in this case. Another example is this pH millivolt benchtop meter. It will give you pH accuracy with 0.002. As you can see, you can read to the 3 digits after dot, but uncertainty will be 2, not 1. And you can read millivolts with millivolt accuracy of 0.1 millivolt. This device can also read temperature with relatively low accuracy, plus minus 0.1 degrees Celsius. Another important unit is relative uncertainty. Relative uncertainty is absolute uncertainty divided by magnitudes of measurement. Sometimes we, instead of saying relative uncertainty, we say fractional uncertainty. Another common way to say this exactly the same thing is relative standard deviation. So we are dividing standard deviation, which is measure of uncertainty, by mean. Some people use percentage. So percent relative uncertainty, that is 100 by relative uncertainty. I strongly discourage you to use this. You'll forget about percent and you'll have 100-fold. So when we do some simple arithmetic operations to uncertainty, how they will change. If you add or subtract numbers, first, they should have exactly the same units. You cannot add milliliters to liters or seconds to hours. You need to use the same units. Second, doesn't matter if it's addition or subtraction. You take your uncertainty, square it, and add all these uncertainties, then take square root. This will be uncertainty of your result A capital. If you do multiplication or division or two of them, you do exactly the same operation with relative uncertainty. Relative uncertainty of your result will be square root of relative uncertainties of each component added and squared. Then you take square root of this sum and you have related to standard deviation or relative uncertainty of your multiplication or division result. We'll do more examples when we start doing analytical calculations.